Hey guys, welcome to Unit 1, Notes 8, our first set of notes in chemistry. First, we should probably describe what chemistry is. What is it that we're going to be studying together? Chemistry is the study of matter. Physics is the study of energy. And everything in the world falls into one of those two categories. So we're going to focus on matter. What happens when you change the type of matter, and what kind of maybe heat release or color change might go along with those changes in the types of matter. So chemistry is study of matter. First thing I want to describe is how science works. So the first thing under that umbrella there is to figure out the difference between a law and a theory. What do you think the difference is between a law or a theory? Well, a lot of people think that a theory is just not as well proven as a law, but that over time, a theory could become a law. That's not quite right. Actually, a theory is the explanation of an event, where the law would simply be an observation of the event. So we have a couple definitions here. The law is simply a summary of an observation, and the theory is an explanation. Keyword there, explanation. Theories explain. Let me give you an example. The law of gravity simply says that if I were to drop this marker, the marker will fall to the ground. Whereas the theory of gravity would explain that the center of mass of that marker and the center of the mass of the Earth are actually attracted to one another, but because of the smaller mass of the marker, there's a greater acceleration. And so it seems as if the marker is falling to the ground, but really it's an attraction between the two center of masses. That explanation is our theory, where the law simply states what happened. So this kind of relates to the way science works in general. We have to first describe what an observation is as opposed to an inference. This is going to be a really big deal in labs, as we need to make observations to back up our inferences about what's going on at a microscopic level. The thing is, chemistry is all about the microscopic stuff. And so we have to see things in the real world and then use that to try to figure out what's going on at a microscopic level. So there's a connection there between what we can observe and what we can infer. So an observation is something that you can see, smell, taste. It's basically using the five senses. It's something that's not arguable. It's something that can't be wrong, because we all saw the marker fall to the ground. We would all smell the same thing. Like, an observation is simply a fact. Whereas an inference is taking your applied knowledge and trying to determine what happened. So for example, we saw the marker fall, but we don't necessarily know why that happened unless we've studied the theory of gravity. And then we learn about attraction and Coulomb's law and things like that that can explain what we saw. Those would then become inferences, as they're made based on prior knowledge. I could see a cloud in the sky, but that doesn't mean that it's going to rain. If the cloud is dark, maybe I might infer it's more likely to rain. But this is all based on prior knowledge. It doesn't mean that I could make some kind of random, unbacked up claim. For example, if you saw an elephant-shaped cloud in the sky, you couldn't assume there's an elephant there. That would be an invalid inference. So there are right and wrong inferences. It does need to be based on something. And this is going to be a big deal when we talk about a hypothesis. Maybe in grade school it was okay to make any hypothesis, any guess, whatever you wanted. But at this level, we need to have some kind of basis for our guess. That's why we call it an educated guess. So an inference is based on prior knowledge. The line can get blurry sometimes between an observation and an inference. An observation has to be an absolute fact, where an inference is incorporating some other knowledge. So the challenge here is, can you identify an observation for this picture? It's tougher than you think. A lot of students say, we have some firemen in the picture. Well, maybe, or maybe those are actors playing a role in a movie to be dressed like firemen. The biggest one is, there was an accident. And yes, it certainly looks like there was an accident, but unless we were physically there, we don't know that there was an accident. Perhaps this was staged. Perhaps this was photoshopped. We don't know because we weren't there. We would just be making an inference based on the fact that we know cars don't typically stand up straight like this unless something happened. So observation versus inference is a little tricky. Our goal with labs is to make observations based on fact, apply the laws and theories that we learn along the way, and then produce valid inferences or hypotheses in our experiments. It's just kind of how labs work. So speaking of labs, let's talk about some variables and controls. How do I perform an actual controlled experiment? So a couple of important definitions. The variable is something that changes, and there are two main types of variables. First of all, we have our independent variable, something that's being manipulated or changed on purpose. This is the thing that you're deciding to test. Then we want to look at what changes in response to that. We call that the dependent variable because it's dependent on the changes in the independent variable. And for any controlled experiment, you should only be testing one independent variable at a time. So if there are multiple things that could affect the dependent variable, we want to make sure we control them. A controlled experiment would only test one thing at a time. For example, if we're trying to see what's going to produce plants that grow more quickly, we wouldn't want to test types of soil, amounts of light, amounts of water, all at the same time. We would pick one and control the other factors. So those are the controls, the things that stay the same or are constant. Then we change only one thing in order to measure the response of that thing. There's one acronym I want to go over here while we're talking about variables. And it's kind of helpful, especially once we get into graphing variables. It's called dry mix. So the D stands for the dependent variable, and the I would stand for the independent variable. And you'll often see these abbreviated in this class as DV or IDV on some of your lab worksheets. The R stands for responding. So the dependent variable responds to the independent variable, whereas the independent variable is the thing that is manipulated or changed on purpose. So we change the independent variable and we look at how the dependent variable responds. It does matter what goes on the X or Y axis. So typically your independent variable goes on your X axis, and then you would graph the responding variable as a function of what's on the X axis by putting it on the Y axis. And so that's typically how you're going to set up your graphs when we do labs so that we can see how the independent variable is affecting the dependent variable. Is it linear? Is it exponential? Is it increasing like a direct relationship or decreasing like an inverse relationship? That graph can actually tell us a lot. So we want to make sure we get the variables in the right places. All right. So we've got our different types of variables, and then the rest are controls. Scientific method is something that's probably a pretty strong factor in your science background, something that you probably study every year you take science. I don't need you to memorize these exact versions of the steps. I just need you to be familiar with the overall idea of the scientific method and to be able to apply it in the lab. So the first thing that you typically do when you're starting to study something is say, hey, that's weird. I wonder what's going on over there. So you have to see something that you want to investigate, but then you have to put it together into an actual testable question. So we formulate something called a research question, the question that we want to research. Then we're going to form a hypothesis, and a hypothesis has to have a basis. It's not okay just to take random guesses anymore. You have to have an educated guess to form a hypothesis. So emphasis on educated. All right, then we're going to actually conduct our experiment. We want to make sure it's a controlled experiment. So think about everything we just talked about with the variables. While the experiment is going on, we want to make two different types of observations. We want to make both qualitative observations and quantitative observations. And what happens at this level more than often than not is everyone gets so focused on the quantitative observations and the calculations, the hard part, that we forget about the qualitative observations. But they can actually be the key to understanding where the experiment might have gone wrong a little bit. We have something called sources of error, which describes kind of innate problems with the lab. And so your qualitative observations can actually be the key to unlocking what your sources of error are. We want to make both qualitative observations, or observations based on the quality or description of the substance, and then quantitative observations, numerical numbers, masses, things like that. So once we have all that data recorded, then there's an analysis process. This can involve calculations or graphing or a combination of both, something that's going to allow us to reflect on the data and answer our initial hypothesis, to confirm it or to refute it, support it or not. So that would be our conclusion, where we need to kind of reflect all the way back to the hypothesis and determine if our data supports or doesn't support the hypothesis, and make that very clear with a very clear, blunt sentence at the end. This data does not support the hypothesis, or vice versa. But that's not the end. And unfortunately, that's the biggest mistake with the scientific method. Even though you hear about it every year, it's like, what is my question down to what is my answer? And people forget it's a repetitive process. But that's the most important part. You have to then take that conclusion and reevaluate it. Does it need to be verified further? Maybe multiple trials. Does it need to be shared and reevaluated for, hey, why was this such a failure? Why did I get such a large % error, or part of the experiment that was wrong? Why wasn't my hypothesis correct? What else could be going on? So those questions and new findings are going to be what spur scientific advancement further. So that's actually, in my opinion, the most important part of the scientific method. Even if the experiment fails, could it still give us some information to move forward and make further advancements in another area? Maybe it didn't answer this hypothesis, but maybe it spurs a new idea for another experiment. So that's kind of the cool part of the scientific method, is it is supposed to be a repetitive process, constantly leading to new and better questions. All right, so now let's focus on the data part. When we collect data, we need to make certain measurements. And it's kind of important that all scientists around the world are on the same system. Some parts of the world use the metric system. For example, with temperature, we don't all use Fahrenheit around the world. A lot of parts of the world use Celsius. We really need to be on the same page if we're going to collaborate or work together as scientists. So scientists a long time ago adopted something called the International System of Units, or SI units. International system is actually backwards because it originated in France, and so in French, the adjective comes after the noun, similar to like Spanish, some other languages. So we call them SI units, but it really stands for International System. It's a system to make sure that all scientists are working on the same page, and so you don't have conversions leading to huge problems. For example, a satellite not making it to space because somebody messed up a conversion. If we're all working in the same units to start with, we won't have those problems. So I want to go through a few measurements and what the SI units are. The first one is length. So length is typically measured in meters, and length describes the distance between 2 points. How far does it go from point A to point B? Just a one-dimensional unit. Then we have volume, which actually would describe a three-dimensional unit. How much space total is occupied by something? And the unit for that is liters. Now, you may notice that these are largely the metric prefixes, and it does tend to kind of be a pattern. So then the question is, what if you add a metric prefix onto these units? Would it still be considered the international system, or the SI unit? And the answer is yes. We could have not just meters, but centimeters, still the SI unit. Not just liters, but milliliters, still the SI unit. Whereas if we changed it to gallons, that's not the SI unit. That's a completely different conversion. Next one is mass, which is the amount of matter. Now, matter is the amount of stuff. So how much stuff is in an object can be measured by its mass. And the mass does not change dependent on gravity, unlike weight. So this is one of my biggest pet peeves, to be honest with you, is using weight and mass interchangeably when they actually mean two different things. Weight is actually a force, so it's going to be measured with a different unit, something called newtons. And that force is going to describe how much gravity is pulling on the substance. And yes, if I have more matter, it would have more gravity pulling on it and the weight would increase. So weight and mass are directly proportional, or one would increase, the other would increase. But we aren't studying forces, that's physics. So I don't want to hear you using weight when you mean mass. It can be a little awkward to get used to, but you would use mass in the same way that you would use the word weigh. I want to weigh the object. I want to mass the object. What is the object's weight? What is the object's mass? It works exactly the same way, and our units will always be grams. Scales measure mass. And so we want to make sure that we are using the correct terminology and not using weight, because we aren't studying forces in chemistry. All right, next we're going to talk about two different definitions, precision and accuracy. A lot of times these two terms are actually used interchangeably, almost like synonyms, but they actually have a slightly different meaning. When I talk about accuracy, I'm talking about how close to the correct answer I have. So for example, if I'm doing a lab and I'm trying to determine the density of an object, if I can look up what the density is, compare it to that value, I can determine how accurate my answer was or how accurate the lab was. And there's actually a calculation for that we're going to do later called percent error. There's a difference when I talk about precision. Precision doesn't actually describe how close to the correct answer I am. What it describes is how exact my answer is. So this kind of translates to having more decimal places. For example, the numbers 25 and 26 sound close together, but the numbers 25.4 and 25.5 are a lot closer together. So how close together we are is actually our definition for precision. And we can only tell how close together we are if we have more decimal places. So a more decimal placed number, or a number with more decimal places, would actually be a more precise measurement, something that was taken to a greater degree of exactness. So they can kind of sound similar, so we have one more way to kind of describe that, and this is an analogy using darts. So let's start up in the top corner. This would indicate the greatest accuracy and the greatest precision, where all three darts thrown hit the bullseye exactly and they are super close together. If I go down from that, I am right around the target range, but they are not really close together. So that would indicate high accuracy, but low precision. Whereas the top corner would be the opposite. Notice how the darts stayed together, high precision, but they're now far away from the target, so very low accuracy. And then in this corner here, we have something trying to represent both having them far apart and far from the target, low in both respects. So this hopefully drives home the idea that getting it right means being accurate. Getting the same answer over and over again indicates high precision. All right, now we're going to move into the calculations part of these notes. So the first calculation that we're going to look at is density. So density is essentially a ratio of how much mass is in an object per the volume that it takes up. So if I, for example, have a substance that takes up the exact same volume, and I have objects that are taking up a lot of the space, this would have a higher density because the objects are taking up more mass per volume, whereas this one has less mass per volume. Pretending I drew equally sized squares, which I'm sure they're not exactly equally sized, but close enough. So the point here is that density tells us how close together the molecules are, because it's a mass to volume ratio. So let's look at an example where we're going to actually use this as a formula. Density equals mass divided by volume. In this example, I'm trying to find the mass, and I can tell that because it asked what is the mass. So mass is my question mark. And then I have 10 milliliters. Now we're going to see a lot of word problems in this class. The easiest way to match up the number with the correct variable is the units. So the units are what follow the number, in this case milliliters for our 10. So if I say 10 milliliters, milliliters was a version of liters, which was one of the units for volume. So I can tell that the volume, or V, is going to be equal to 10 milliliters. The next thing it tells me is that the density is 3.76 grams per milliliter. So this is a mass to volume ratio. So this must be density. And yes, it does tell you that Just trying to help you see how the units kind of can give it away as well. So the density is 3.76 grams per milliliter. So now there's a couple different ways we can solve this. Plugging into the formula and solving for x is my favorite way. So first let me set that up. 3.76 grams per milliliter. Plugging in for d. On top, the mass is unknown, so I'm going to write the letter m. And we are going to treat these variables like x, but try to get out of the habit of using x for any unknown. Use the actual variable that it's representing, in this case, m for mass. And then on the bottom, the volume, I'll plug in the 10 milliliters. And so you can see to solve for x, or m on the top, I basically need to multiply by 10 here. So the mass is equal to my 3.76 grams per milliliter times the 10 milliliters. And watch what happens to the units. Just like with x, something on the top would cancel something on the bottom. My milliliters cancels, leaving me with grams, which is good because mass should be in grams. And so if you watch your units, you can actually tell if you're kind of solving it right. You should kind of match up the units for your variable. Now for the math, 3.76 times 10, 37.6 grams. And so that's my final answer. I do have a trick with this little triangle that's over here that I want to show you real quick too. And just another way to handle the algebraic manipulation instead of just plugging in. So density equals mass divided by volume. That's basically what this formula is, right? It works the other way around as well. The volume is equal to mass divided by density. Or, when they're next to each other, you would read it as times. So mass is equal to density times volume, which basically rearranges the formula already for us. So mass is the density, which was the 3.76 grams per milliliter times the volume of 10 milliliters. And this is essentially where we were at when we multiplied to isolate m in the first place. So it kind of skips the algebraic manipulation for you, but you have to be comfortable with how the triangle works. Whenever I'm solving for mass, it's density times volume. Solving for density, mass divided by volume. Solving for volume, mass divided by density. And that little triangle trick will actually work with any 3-variable equation. So it's kind of handy. Oh, missed some marker. There we go. So there we go. We have our mass is equal to density times volume, one way or the other. We actually multiply them and let the milliliters cancel, and we have our mass in grams. Final answer. All right, let's work on some temperature conversions next. So there are a few different versions of measuring temperature. The absolute temperature is actually always measured in Kelvin. So Kelvin is the scale that stops at 0 Kelvin, would mean absolutely no movement in the system. Temperature is an average of kinetic energy. Kinetic meaning energy of motion. So if there's no motion, then there's no temperature on our Kelvin scale. The Kelvin doesn't have a negative. 0 motion, 0 temperature would be absolute 0 in the Kelvin scale. Then we have some more common ones in like real life. We usually measure, here in America, we usually measure degrees Fahrenheit for our temperature outside. There are also a lot of parts of the world that use degrees Celsius. And actually that is our unit that we're going to use probably most often in this class, although there is a lot of Kelvin in gas laws. Celsius is going to come up a lot too. But I want you to be able to convert that in and out of what we are used to as well. So the main temperature conversions will be with these first 3 types of temperature. But there is also another one called Rankine, which they actually use in the Navy a lot. So these are the different ways to measure temperature. We're not going to do conversions with Rankine though. So here's our conversions just with Kelvin, Fahrenheit, and Celsius. So in order to get Kelvin, you have to be in Celsius first. So if they gave you Fahrenheit, you'd actually have to convert to Celsius and then convert to Kelvin, or use a system of equations to put the equations together. And then depending on whether you're looking for Fahrenheit or Celsius, there's two different interpretations of these formulas. So 1.8 times the temperature in Celsius and then add 32 will get you Fahrenheit. But if you have Fahrenheit, you have to subtract the 32 first, right? Watch your order of operations, and then multiply by 0.56. You may have seen these formulas before with fractions. We typically don't use fractions in this class. It's usually the decimal version. So it's going to be 9/5 or 5/9. Maybe if that rings a bell. That's what that comes out to in decimal form. All right, now let's look at a conversion example, and we might as well do one where it starts in Fahrenheit. We have to convert to Celsius and then Kelvin, so we can do a couple of the formulas together. So the first question says I have 98 degrees Fahrenheit, and I want to know what it is in Celsius and then Kelvin, and it does have to go in that order, right? So first we're going to plug in the formula, or write down our formula, where the degree Celsius is 0.56 times the degrees Fahrenheit minus the 32. Then we're going to plug in the 98 and subtract out the 32, which is 66. Then, and only then, would I multiply by 0.56. So you want to make sure that you're doing the subtraction first, the parentheses first, and then multiply by 0.56, and we can get our final answer of about 37 degrees Celsius, 36.96 degrees Celsius. But then we want to convert it to Kelvin also, to answer the second part of the question. So if I'm starting with my degrees Celsius, all I have to do to convert it to Kelvin is add 273. So I'm going to take my Celsius temperature, add 273, and I get 309.96, or about 110 Kelvin. So now I have my temperature both in degrees Celsius, or 37, and Kelvin, or 310. Converting first to Celsius and then to Kelvin. The next calculation that I want to go over is called percent error. Percent error essentially describes how accurate your answer was. This is typically used in a lab situation. So we would have something that's measured. I sometimes call this the experimental value. Whatever you get as your result in a lab, we want to then compare it to its accepted value. What is the actual density of an object, and what did I figure out that it was using data? So I want to compare how far off they are. So notice the subtraction here, like how far away am I from the right answer? And then I want to find that as a ratio to the right answer. So you're basically going to find the difference in the two numbers and then divide it by the right answer. Notice that we have absolute value bars here. That means it really doesn't matter what order you subtract in. You're just looking for how far away your answers are. If you happen to get a negative number, you just ignore the negative. That's what you do for the absolute value, right? And you divide it by your actual value. And then since it's a percentage, we're also going to multiply it by 100. We want low percent errors. We want a high degree of accuracy, meaning we want to be very close to the correct answer. So the ratio of how far off we are to the right answer better be pretty small. So let's look at an actual experiment. Here we have the density. When we perform an experiment, we determine it's 19.20. So if we determined it, that would be our measured or experimental value. But then the actual density is given to be 19.3. So we're a little far off, right? That 19.3 would be my accepted value, what the actual density is, not what we determined in a lab where we have sources of error, but what it really truly is. So we want to determine how far off we are. So I'm going to plug these numbers in, plugging in the accepted value on the bottom and then finding the difference between the two on the top. So plugging in like this. So I'm looking at the difference between 19.30 and 19.20. So that would be that would be just a difference of 0.1, basically. So that's what I have on the top here, this 0.1, and I'm going to divide it by 19.30. I want the ratio of how far off, I was only 0.1 off, and compare that to the actual answer. So 0.1 divided by 19.3 is 0.005. But then we want to find the percentage, so we're going to multiply by 100. So if I do that once, I get an answer of 0.5. One of the most common mistakes that I see is taking that 0.5 and multiplying by 100 again. We already multiplied by 100 once to get 0.5, so there's no reason to multiply by 100 again. And I think the reason for that is because people don't expect such small percent errors. The smaller the percent error, the better. We want a low ratio of our error to the right answer. So we want the lowest percent error possible. So 0.5 is great. That must have been a pretty successful lab. Last thing that we're going to cover in Notes A is some ideas behind graphing. So we're going to go over 3 main types of graphs and the types of things you should include in all of your graphs in this class. So there are 5 main things to include in a visual representation of data. Some way that we are trying to demonstrate how the X variable affects the Y variable, or how the independent variable affects the dependent variable. So what are some things that you've created before? What are some things that you've put on graphs before? So one thing that's really important is the title. We want to actually make sure that we understand what the graph is trying to represent. What is the visual representation? So for that, we need a title. And we do actually need a correct title for a graph. So by that I mean you need to describe your variables. You need to determine or describe what the independent variable and dependent variable are. You can't just say graph of data. That is no longer a valid title. That's something that we need to kind of improve on and make sure that we actually describe what the graph is showing. The next thing that we want to make sure we do is label what our X and Y axes are. And remember, the X axis with dry mix would be the independent variable and Y would be the dependent variable, dry. So we want to make sure we get the variables on the correct axes and make sure to label them completely. You don't abbreviate the label. For example, temperature, you need to write out, not just write temp. Write out your label. The other thing we need is the units. Now, units are supposed to be abbreviated. So for example, you need to actually find the degree sign with the capital C for degree Celsius. You shouldn't write out the words degree Celsius. So not ever abbreviated, always abbreviated. That's the correct format for your axes labels. The other thing that we need to make sure we do is set the scale correctly. And Excel and other graphing programs will tend to do this for you. But if you're ever making a hand graph, you want to try to make sure that you don't go from 10, 20, 30 up to 100 and make that look the same. Then you're going to miss your exponential versus linear analysis and things like that. So you want to make sure the scale is evenly spaced along both X and Y axis. And then the last thing is only needed sometimes. You need a legend or a key only when appropriate. So when is it appropriate? Well, it would only be when you have multiple trend lines, multiple trials that you're putting on the same graph. Excel has a bad habit of putting in a legend for you and just labeling it series 1, and then it's just there in the way. That's bad communication. You shouldn't just leave something there that doesn't belong. So you want to make sure that you delete that if Excel's trying to help you out. It's really distracting. You only want to include a legend when you actually have multiple trend lines on the graph. And that actually doesn't come up a whole lot in this course. All right, now let's talk about the 3 different types of graphs. So this actually is an example of a line graph. In a line graph, you still put the independent variable on the x-axis and the dependent variable on a y-axis, but the line graph actually plays connect the dots. This is actually a little bit different from the graphs that we typically use. Let me make some room for me to write here. How about down here? So typically, we have our independent variable on our x-axis and our dependent on our y-axis. And we're going to graph typically about 5 data points. And we're going to insert a line of best fit, which Excel will call a trend line. So this is actually called a scatter plot, where we've inserted the line of best fit. See the difference here? And the line graph actually connects the dots. So I'm going to be careful that we're not calling this a line graph, because it's not actually exactly what it is. But either one can show kind of how data changes over time, or how the y variable changes in response to the x variable. The most common type of actual line graph, or connect the lines type of graph, is actually going to measure changes over time. So time is a very common independent variable. And then we'll see how time affects different things that we can put on our y-axis and show that relationship as we kind of connect the dots and put things together. Next type of graph we have here is called a bar graph. So a bar graph is good for comparisons. For example, if you do multiple trials, you could put the data next to each other and you could show variations between trials or show high precision, show them being close together. Bar graphs are also good for background sections of lab reports because you can do things where you're comparing, like, look at all of these. What is it in this case? The heart disease is so bad, so that's why I decided to investigate heart disease. So it's good for kind of that background of why the experiment is important in the first place. Last but not least, we have pie charts. And pie charts are the best thing for showing parts of a whole. Things like demographics, things that are parts of who likes these TV shows. This many percentage of people like the TV shows. So whenever you want to show like how much of a group cares about one thing, or how much of a group acts one way or does one thing, you're looking for parts of a whole. A pie chart is a good kind of go-to graph. And again, that's usually pretty good in background sections when you're trying to emphasize why you're investigating a specific thing. All right, that's going to do it for Unit 1 Notes A. We've gone over quite a few things. We've talked about how science works. We talked about different types of calculations that we're going to kind of start with and be kind of important conversions to start with. And then we talked about graphing as well. So I hope this gives you a good introduction of what we're going to be working with in chemistry. The next set of notes is called Unit 1 Notes B, where we're going to talk about more calculations. We're going to talk about scientific notation. We're going to talk about something called dimensional analysis or more conversions. It's going to be a very math-based unit. So we'll see you there.